Today I'm going to talk to you about a new kind of geometry. It is different from the kind of geometry that you have studied in schools. However, it is really not an unusual kind of geometry in the sense that this geometry is all around us, even inside us. This really is the true geometry of nature. Benoit Mandelbrot, the person whom we can consider to be the father of this kind of geometry, had once famously said, clouds are not spheres, mountains are not pyramids, the coastline is not a circle, lightning does not travel in straight lines. What he was trying to say is that the kind of objects that we see all around us do not really conform to the standard of this nice geometry of Euclid's, made out of straight lines, spheres, circles, and so on, but rather to an entirely different kind of geometry. A beautiful kind of geometry, but a very different kind all the same. Before we go on to talk about the more technical aspects of this geometry, let me just show you a few examples to convince you that this geometry is really all around us. As I said, fractals are all around us. Take a look at this picture. If you look carefully, you may be able to recognize that every small piece of this picture essentially looks a bit like the whole thing. In fact, if you took a small piece out of this picture and blew it up under a powerful microscope, you will actually see the same structure repeat. In fact, what you are seeing right now is also of the picture taken by a powerful microscope. It's actually the vegetable broccoli. In fact, if you took our humble cauliflower and did the same, you will see a structure very similar. Of course, not green in color in that case, but white. So this is the kind of structure that we are talking about, fractal structure. Well, you see another example of fractal structure here. These are salt flats. And of course seen from a very big height, from an aeroplane. If you look closer, you will see many tiny waterways, and you blow them up in the picture, you will see again the same kind of structure repeating. Now this particular picture is from Arizona, but our Koch, run of Koch in Gujarat essentially has the same kind of structures. This is an example from an ammonite shell. Again, you can see that this wiggly pattern repeating at every scale. In fact, if you took a small piece out of this and blew it up, you will see structures very much like the whole thing again. This is a picture of our very own Himalayas taken from a plane. And I don't really want to repeat this over and over again, but you can see the same thing repeating at every structure, at every level. This is something from our plant world, a fern, and here is a picture of clouds. And you can even see that here again. If you take a very small piece out of this, blow it up, this blown up picture will look very much like the whole picture. You see this repeating theme again in leaves, in an aerial view of the Amazon, in the Grand Canyon, in lightning strikes. If you took one of these small branches of the lightning strike, blew up its picture, you will again see a replica of the whole thing. I don't need to tell you what this is. These, of course, are snowflakes. There is a waterfall. The repeating nature is visible over and over again. And not only are fractals all around us, they are actually even inside us. This cutout view of our lungs. And as you can see, our lungs is not really a solid geometrical structure. It's made out of many tiny pieces, And these alveoli are what are responsible for exchanging oxygen and other gases and keeping us alive. And you must realize that the only reason why we can function, live and breathe is because this extremely intricate structure of the alveoli allows us to have a much huger surface through which we can exchange oxygen with our blood, and it's essentially because of this extremely intricate fractal structure that we can live. If lungs had been made out of solid geometrical patterns, the surface area would have been way too small for us to be able to breathe enough oxygen to function. A close-up picture of our eye. Again, you can see something very similar to what you saw in the run of Koch or in the Grand Canyon. Our neurons are interconnected in a massive way, and again, small pieces of this picture blown up looks like the entire picture. Well, not only are fractals all around us or inside us, well, there are also things which our future may be built of. Already a lot of engineering is taking fractals or the geometry of fractals into account, and I'm just going to leave you with this one picture. There's a artist impression of what a futuristic bridge on the Hooghly could look like, and who knows, maybe this will actually adorn our skyline one day soon. But enough of pictures, let's get back to the actual technicalities of the subject. Don't worry, I'm not going to make this very technical. So, the first thing that we should perhaps do whenever we are talking of a mathematical subject like a geometry, fractal geometry in this case, is start with a definition of what we are talking about. The problem is, ever since this term fractal was coined in 1975 by Benoit Mandelbrot, the person whose quote I talked about a while ago, people have tried to define fractals in many ways, and we have many definitions of a fractal. For example, we have this definition, a rough or fragmented geometric shape that can be split into parts, each of which is at least approximately a reduced size copy of itself. Or a geometric pattern that is repeated at every scale and so cannot be represented by classical geometry. Well, or even something as short and sweet as an object with a fractal or fractional dimension. Now, the trouble is, most of these definitions fall short in one way or the other. They capture some properties of fractals, they don't capture some other properties. And rather than be very rigid about defining what exactly a fractal is, what we are going to do now is we are going to start off with a few examples which will help you understand what we mean by fractals. So the very first example that we will start with is a very famous classical fractal. It's called the Koch curve, and here I am going to explain to you the process by which you can create or at least imagine a Koch curve. For this, you have to start with a line segment, just a simple old straight line. Nothing can be much simpler than that in geometry, but what you do next is amazing. This straight line is called a level 0 Koch curve. Well, it's the 0th iterate in the formation of the Koch curve. We first trisect the curve. I hope you can see this clearly here. I have broken up the original black line into 3 pieces. Now I have a black line, a red line in the middle, and a black line. You then drop the middle segment and replace it by 2 sides of an equilateral triangle that you would have drawn on it. So although I have retained the red line in the picture, that's just a guide to the eye, what has happened here is that what was originally a straight line has become this zigzag line. So this gives us what is called the level 1 Koch curve, the first iterate. Now you have to repeat this again. The level 1 Koch curve is actually made out of 4 line segments. You do the same thing to each of the 4 line segments. You trisect each one of them, rub the middle third, and replace that by 2 sides of the equilateral triangle. So now you have a structure which looks like this. Well, you don't stop here. You now have more line segments. You do exactly the same thing to all of them and keep on doing this over and over again. Now, none of these really is the Koch curve. Only the final version that you will get after infinitely many iterations is the actual Koch curve. Of course, when you're doing this on a piece of paper or even using a very powerful computer, you cannot do this infinitely many times. But if you do it 5 or 6 times or a few more times, depending on how accurate you want to be, you will get a pretty good estimate of what the Koch curve looks like. This picture essentially here is not, of course, of the final Koch curve, but it's a very, very decent approximation of that. Now, this Koch curve has wonderful geometric properties. Let us explore a few of them. First, it's obvious that it is continuous everywhere, right? After all, you can draw this curve, in principle, from one end to the other without ever lifting pen from paper. However, if you go back to the stages of making up the Koch curve, let's say this one, you can see that although this curve is continuous everywhere, it is differentiable, but only inside these line segments. At every corner, it fails to have a unique tangent, which means that this curve is differentiable, well, almost everywhere, but not at these corners. But notice that as you go further and further down and repeat these iterations over and over again, what happens is that the corners keep on growing in number until in the final iteration there are corners everywhere. What that means is that this is a curve which is continuous everywhere but differentiable nowhere. When this was first discovered, or when functions like these were first discovered in the 19th century, not the Koch curve, but another much more mathematically intricate function was first discovered. It was continuous everywhere, but differentiable nowhere. It came as a very rude shock to the mathematics world. Most mathematicians tended to believe that continuous curves can fail to be differentiable, but at most at maybe finitely many points, or even perhaps countably many points if you know what that is. But a curve that is continuous everywhere but differentiable nowhere was something people could not imagine at all. But the Koch curve is a member of one such of this family, a family of curves which are continuous everywhere but differentiable nowhere. Now, if you take a third of the curve and blow it up, magnify it by a factor of 3, what you will get is the whole curve. By the way, if you look back at the stages of formation of the Koch curve, it should be pretty easy for you to figure out that if you took, say, the stage 4 Koch curve, took a third of that and blew it up by a factor of 3, we will actually not get the stage 4 Koch curve, we will get back the stage 3 Koch curve. In general, blowing up by a factor of 3, 1/3 of the level n Koch curve should give you the level n minus 1 Koch curve, the previous level. But after all, our actual Koch curve is what you get after infinite iterations. So if you blow a third of it up, you are going to get exactly the full curve. So this is exact self-similarity. You have seen examples of this self-similarity in all the pictures that I had shown you before, but they were of course approximately self-similar. Nobody would really tell you that if you took a small piece of the lightning picture and blew it up, you will get exactly the same picture as the whole lightning, you'll just get something which looks very similar. The Koch curve, on the other hand, is geometrically defined and is exactly self-similar. Okay. Next, let us try to ask ourselves how long the Koch curve is. Notice that at the beginning we had just this black line. Let's call this 1 unit long. In the next iteration, what happened was we dropped the middle third but replaced that by 2 equal sides. That means we now have 4 sides in our Koch curve, level 1 Koch curve, each of length 1/3. That means that now I have a curve whose length is 4/3. Now this increase by a factor of 4/3 will happen at every stage, because at every stage what we are doing is taking every line segment and replacing it by something which is 4/3 as long. So if you keep on increasing the length by a factor of 4/3 every time, and what that means is that as you keep on going, the length of the curve keeps on increasing without bounds. The length of the final Koch curve is infinite. And that's really rather startling if you think about it, because the curve fits into this very small region. It never strays out of this small area here. Yet it's infinitely long. But now let us ask this question by turning it on its head. How long really is the Koch curve? When I say really, I mean if you were to measure the length of the Koch curve by some measuring instrument, maybe a ruler, how long do you think it will come out to be? Of course, the numerical length that you get for the curve will depend on the size of your ruler. If your ruler was just 1 unit long, it will fit from one end to the other of the Koch curve. And if all you ever had was a 1 unit long ruler, you would have to say that the length of the curve is just 1. However, if you had a smaller ruler, which is 1/3 unit long, now how many such rulers can fit and cover the entire curve? The answer is 4 of them. So, if you are using a ruler whose length is 1/3, the total length of the curve that you get, that you can measure, is now 4 times 1/3. In fact, if you cut down the length of the ruler by a further factor of 1/3, you can now follow some of the bends which you could not follow earlier, and now the number of line segments that you will need, or rulers that you will need, is 16, 4 times more than before. And each time you keep on doing it, each time you reduce the length of your ruler by 1/3, the number of rulers you need increases by 4. Now, if you think about it, if you wanted to measure the length of any ordinary curve using a ruler, then if you cut down the length of the ruler by 1/3, you may need more than 3 of them at the beginning, because a small piece may be left out after you just try fitting 3 lines. That's because now that you are using a smaller ruler, you can follow the bends more. But it should be easy for you to guess that once I make the ruler small enough, after that, cutting down by a factor of 3 the length of your ruler would mean you will need 3 times as many rulers. Now this is intricately connected with the notion of dimension. For ordinary curves, this factor, the number of rulers you need when you cut down the length of your ruler by 3, should be 3, which is just 3 to the power 1. As I said, that it may not be 3 at the beginning, but once you make the ruler small enough, it has to be 3. Okay. Notice that I have written 3 as 3 to the power 1, and there's a reason for that. To understand what that reason is, let's look at a 3-dimensional object, or first a 2-dimensional object, a plane figure, let's say square. To cover the square with other squares, each of which is 1/3 as long, we will actually need 9 squares, which is 3 square. If you had a cube, well, I don't have a picture of a cube here, but just imagine the Rubik's cube, and The Rubik's Cube is very well suited for this, because if you look at it, it looks like it's made out of 27 smaller cubes, each with length 1/3 the length of the original cube. And so for solid bodies, cut down the size of each cube linearly by 3. You need 3 cube times as many. So what are these numbers 1, 2 and 3? These are what we call dimensions. At least one sense of the word dimension can be found from here. Well, for our Koch curve, it so happens that if I am going to call this power the dimension, we must have this result. 3 to the power d is neither 3 or 9 or 27, but is 4. What that means is, if we take the log of this expression, we can easily figure out what d is, and d turns out to be log 4 over log 3, 1.2618, etc. This is the so-called fractal dimension of the Koch curve. You notice that this is not an integer, so this is very different from the kind of dimensions that we think about. In fact, the kind of dimension that we usually think about is technically called topological dimension, and the technical definition of fractal is any object whose fractal dimension, defined this way, differs from its topological dimension. The topological dimension of the Koch curve is 1. It's a curve. You can bend and stretch it into something which looks more like ordinary curves. So the topological dimension 1, but fractal dimension 1.26. They're different, so this is a fractal. Now, let us give you one more example of a fractal. This one is very, very important in basic mathematical analysis. This is called the Cantor dust or Cantor's fractal. For this, you again start with a line segment, but this time think of the line segment as a part of the real line, the closed interval 0, 1. When I say closed, I mean both 0 and 1 are part of this interval, and you are talking of all numbers in between. Now, well, you begin almost like the Koch curve by dropping the middle third, but that's it. You don't replace it by anything. So now you have two line segments. So closed interval from 0 to 1/3, another closed intervals from 2/3 to 1, and 1/3 to 2/3, this open interval, that is numbers which are more than 1/3 and less than 2/3, they are being dropped. But if you have learned anything from the previous example, you would realize that you wouldn't stop here. You would keep going. Now you have two line segments or two intervals, drop the middle third from both of them. Now you have 4, drop the middle third from all of them. Keep on doing that over and over again. After infinite iterations, you get what is called the Cantor set or Cantor's dust. Well, how long is the Cantor dust? Or how big is it? First you throw away a length of 1/3, right? Next time, you throw away 2 pieces, each of length 1/3 square, so 2 by 3 square. Next time you throw away 4 pieces, each of length 1 by 3 whole cube, so 2 square by 3 cube. So if you keep on going this way, it's easy to see that what you are throwing away in total is 1/3 plus 2 for 2 pieces into 1 by 3 square, plus 2 square for the number of pieces into 1 by 3 cube for the length, plus 2 cube by 3 to the 4, and so on. And this, of course, is what is called an infinite geometric series. And it's pretty easy to add this up. Every schoolboy knows how to find the sum of this. And the sum of this infinite GP is 1/3. That's the first term, into 1 by 1 minus the common ratio, which is 2/3. And the answer turns out to be 1. So what is the net length of the dust? You have thrown everything away. So the net length of the dust, or the measure of the dust, if you want a technical term, is 0. So the Cantor dust is so fine that it has no length left whatsoever. Yet it not only has an infinite number of points, we can prove that it has an uncountably infinite number of points, which means that it actually has the same number of points in some sense in a very strict mathematical sense, as the entire interval that you started out with. This is amazing. In fact, it happens to be something called a compact set, which is the reason why it's used in honing our intuition about the way compact sets behave. It's a very unusual kind of compact set, and if you want to understand how compact sets behave in general, you would love to take a look at the Cantor dust in detail. This is why it's such a favorite among people who study mathematical analysis. Okay, what is the dimension of the Cantor dust? Well, again, think of how long a ruler must you have to cover it. Of course, if you have a ruler of 1 unit long, one of them will cover the entire dust. But if a ruler length was 1/3, you will not need 3 rulers to cover it, you need only 2. If it was 1/3 square, you will need only 4, and so on. So going by the same definition of dimension that we talked about, 2 is to the power d here, because every time you cut down your ruler length by 3, the number of times that your number of rulers needed grows by is 2, and you end up with d, the dimension, being log 2 by log 3. Here, of course, this log 2 by log 3 is a number which is less than 1. So here you have an example of a fractal again. The Cantor dust is a bunch of points. It has topological dimension 0, but a fractal dimension which is different from that. As a final example of a geometrical fractal, we will talk about something called the Sierpinski triangle. Again, its construction is very easy. You start with an equilateral triangle. You drop the middle triangle. That is, you bisect each of the 3 sides. You now get 4 triangles, 4 smaller triangles. Just drop the middle one. So you have 3 identical equilateral triangles left. And if you have learned anything from the previous examples, you know what to do next. You drop the middle third of all of them. Well, go on and on and on. And after infinite iterations, what you get is what is called the Sierpinski triangle. It should be very easy for you to figure out the fractal dimension of this one. Every time you cut down the length of the triangle by 2, the number of triangles you need to cover what is left increases by 3, not by 4, because you don't have to worry about the middle piece. So dimension is log 3 by log 2, 1.584. This is a 2-dimensional object in the topological sense. This topological dimension is 2, but a fractal dimension is less than that. Again, example of a fractal. Let us now take a look at a way in which we can think of these fractals from a different approach, from something which sounds very different, from the approach of linguistics or language. Imagine that you are dealing with a language which has an alphabet which is very, very simple. It has only 2 letters. What are those 2 letters? F for going forward and G for a gap. So F means you go forward by a length. G means you go forward again, but don't draw a line, leave a gap. So in building up the Cantor's dust, let us play a game. This game is, let's start with one single word. So this word is made out of one of the alphabets, just F. Now, of course, F means go forward. So this is what F means in our picture. And the game that we will play is that from the beginning word, we will build up new words using a specific rule. What is the rule? Well, just imagine that you are building up the Cantor dust. What do you do in the next step? You drop the middle third. So from F, what you get is go forward, leave a gap, go forward. The gap is the middle third. So F becomes FGF. At the next stage, you have to worry about not only what does F become, and F becomes FGF, you keep on repeating, but also what G becomes. Now you might say a gap stays a gap, so G becomes G. G stays G. That will not be entirely correct, because to keep the length unchanged at every stage, what we had to do was cut down the length of the distance of what f means and what g means by a third, right? The first time we had f for the entire thing. Next, when we say we have forward, gap, forward, the forward is only 1/3 as long. So is the gap. So g cannot stay g. It has to become g. 3 smaller gaps to make up the entire length as before. So this is the rule of the game, or these are the rules of the game. F becomes FGF and G becomes GGG. So let's begin. We started with F, the line drawn. Next step, we get FGF. Of course, you have only one F, it becomes FGF, and the picture becomes F forward, gap, forward. Next stage, this F becomes FGF, this G became GGG, 3 G's to make up the whole length as before, then this F became FGF. Well, I can repeat, and this becomes an even longer word, the picture becomes even more intricate, and we can keep on going over and over again. So in this game, what we have created is a set of instructions for drawing the Cantor dust. In fact, we can use this on a computer, especially a computer which has drawing methods, to draw dust fractals, or at least approximations or high-level iterations of fractals for us. Well, can we play the same game with the Koch triangle? Well, or not really the Koch triangle, the heading is slightly wrong. I meant the Koch curve. We will talk about what the Koch triangle is soon. For the Koch triangle, you need a slightly more complicated language. The alphabet is not 2 letters, 3 letters. Well, one letter is F for going forward as before, but the other 2 letters are L for turning left through 60 degrees and R for turning right again through 60 degrees. And let us see how this special language of ours is going to help us to create the Koch triangle. Well, we start with the F. You just go forward all the way. The next stage, what do? You go forward by 1/3 the length, but you go forward. Then remember you're facing this way. So then you turn to the left through 60 degrees so that you now face this way. So FL. Then you go forward, FLF. Now you're facing this way. If you turn right through 60 degrees, you'll end up facing this way. You want to go down, so you turn right twice. FLFRR. Now you're facing this way. You go forward. Another F. Now, in order to face horizontally again, you have to turn left through 60 degrees and then go forward. So to replace the original straight line segment with this zigzag segment, what you need to do is replace the F with FLF, RR, FLF. Of course, at the very beginning, in the first stage, you had only F, so you had to worry about what happens to the F. But after that, the bigger and bigger words that you will get will also have L and R. And how do they change? The answer is they don't change at all. Because all you need is L should stay L, LF turn should stay LF turn even in the next stage, R should stay an R. So this is the rule. Just start with a F and at every stage replace all the F's that you have in the previous word with the string FLF, RR, FLF. So you do that, it becomes a much longer string and it keeps on becoming very much longer. I am not writing the subsequent strings simply because the subsequent strings will become too long to write here, but it should be easy for you to see that this is exactly how you can build up higher and higher stages of the Koch curve. Again, something which you can create very easily using a computer program. Now, this language is something which is not really new. Linguists have been studying artificial languages like this in a quest to understand human languages as well as other artificial languages like computer programming languages for a long, long time. Now, this particular language is called L-system language. This is a string rewriting system in which you start with a string, a bunch of characters, you replace them according to certain rules and bring up new words. Now, this was first discovered not by a linguist but by a Hungarian theoretical botanist, Aristide Lindenmayer. That's why these are called L systems, after Lindenmayer. And what was he trying to do when he created this system? He was actually trying to understand how plants grow. While looking at plant growth, he realized that branches essentially are like the entire tree, just miniature versions of that. And there's a fractal structure which keeps on repeating and repeating and repeating. And he figured out that this kind of string rewriting that we have just described is exactly what is needed to describe fractal growth of plants. Not only plants, animal cells, plant cells grow in the same way. And this became a big tool for mathematical botanists to play with. And if you put in sufficiently strong rules, you can generate amazingly lifelike structures. In fact, Lindenmayer is a co-author of a book called The Algorithmic Beauty of Plants that's freely available on the net. If you want, you can download it, take a look at the beautiful pictures. That in itself is a big bonus. On top of that, this book also describes the kind of L-system rules that you need to produce many different fractals. Some geometric fractals like the ones we have described, many more biological fractals, things which look very like real live plants and so on. And if you take a look and try to code this in a computer program yourself, I assure you will find the whole going a lot of fun. We will now take a look at a Python program which implements the L system code that we were talking about. In particular, we will use the L system to draw a Koch curve. The code looks like this. It's pretty small. It's a short piece of code. And even if you don't know the Python language, it should be pretty easy for you to understand what's going on here. The important thing is Python has a module called Turtle, which gives you ways of drawing stuff on a canvas. This is very much like the children's programming language Logo. So here, what we are doing is this. The essential parts of the program are here. This is where we start with the beginning string. We are starting with the word F. Just go forward. We are setting the original length which we asked the user to input to a value. And then I'm going to repeat this n times, repeat a loop n times. That's what this for structure is for. If you knew Python, it would be obvious, but anyway, for I in range n essentially says I takes the value 0, 1, 2, 3 up to n minus 1. That is n values in all, and every time I takes a value, the body of the loop, which is the part which has been indented inwards, this entire part that will work. So what happens in the body of the loop? These are not really very important. These are essentially meant to lift the pen up from the canvas so that the turtle, something you will soon see, will move on the screen without leaving a mark. You are pushing it back to one side by using the goto command. Then you are putting the pen down so that subsequently it's going to leave a mark. And then when you have a word, you want to translate it in pictures, and that is what this thing does. When you say for x in S, x takes the values of each character that is there in the word S, and if that character is an F, It asks the turtle to move forward through a length L. Else if, elif is short for else if. So if x is not f, then it comes here. Else if x is L, then it turns left by 60 degrees. And of course, since our language has only 3 letters, F, L and R, if both these, the if and the else if fails, then the only possibility that is going to be tackled by the else block is that the character is an R, and then you are going to turn right through 60 degrees. And this is where the magic of the else system works. Every F in the string is replaced by FLF, RR, FLF. And here, what we are doing is simply cutting down the length by 3 to remind ourselves that at every next step that we take, every next iterate of the Koch curve, the length by which we go forward has to be cut down by a factor of 3. That is essentially all there is to the code. So the real work is done just here, in these few lines of code. And now let me show you how this works. So I call the Python code by saying Python followed by name of the code, which happens to be Koch2.py. Of course, there was a Koch1.py in the same folder. So it's asking me for the number of levels. Let's keep it short. Let's say 5. Much more than that, and it's going to be very, very slow. Let's enter the length parameter. 600 is a suitable length parameter for the size of the canvas that we will get by default. And here, this is my level 0 Koch curve. The first time the loop has run, it has drawn the level 0 Koch curve. Let me just move this to the middle so that you can see this clearly. Okay, let me hit enter. There's a level 1. So the string f has become FLF, RR, FLF. And my turtle has dutifully used the if, elif, else block to follow that. Again, a new bigger string, a more complicated curve. And I'm going to show you one more level. Of course, it's going to take a long time to draw this, basically because it has many, many pieces to draw. I could have sped up the turtle by using an option. I didn't do it here because I wanted you to see the Koch curve in the making. As you can see, the turtle is following this FLF, RR, FLF kind of instructions studiously and repeating it over and over again. That's exactly what a computer is very good for. And even at this stage, which is level 4, I have a reasonably decent picture of the Koch curve. And now we are done. Okay, let us now go back to our presentation and talk about a different way in which fractals can be generated. So this is the work of Barnsley, who has a wonderful book called Fractals Everywhere, which despite its rather catchy name also happens to be a rather technical book, has beautiful pictures, but also some rather awesome maths to go with it. And here, in that book, as well as in a few papers, he had described this amazing way of creating fractals. There's a copy machine. How does this work? Let us illustrate with the Sierpinski triangle. We start with a solid triangle, and then we make 3 copies, each reduced by a factor of 2, and shift the copies so that they sit on top of each other. Of course, you recognize what this is. This is level 1 of the Sierpinski triangle. But you don't stop here. As always, you repeat. What do you repeat? You make 3 copies of this, shift and paste, and you've got the level 2. Do that again, and you will get the Sierpinski triangle in the long run if you keep on doing this infinitely many times. What is perhaps amazing is this. We started with a triangle here, so it was rather easy to see that the Sierpinski triangle would emerge. But let us start with something else. What happens if I start with a square? Okay, this copy and shift process. The triangle immediately gives me this. I've put in 3 different colors just to help you identify what goes where. The square, on the other hand, does not really look like the Sierpinski triangle at all. There's no gap here, it's just solid. But then we make 3 copies, shift and paste as before. And now we are getting something which is still not very much like the Sierpinski triangle, but at least has a gap. But if you keep on going over and over again, on the left we have triangles only, on the right we have squares. If you keep on doing this over and over again, this copy and shift thing, what you are going to get in the long run is what is called the stable attractor of this set. So whatever you start with, it goes and ends up at that, and that attractor, you've guessed it, is the Sierpinski triangle. So you essentially apply the same function over and over again, but not one function, it's actually a collection of functions. Mathematically speaking, this is called an iterated function system. What we have done here is we have started with a set which is a subset. So here we are getting a bit mathematical, but it should not be too difficult to follow. The subset of what is called the direct product of 0, 1 with 0, 1. This is simply a unit square. A square in your coordinate plane which stretches from 0, 0, 0, 1, 1, 1, 1, 0. These are the 4 vertices of a square. And what we are doing is starting from any set which is inside that. And then we are applying 3 functions. If you think about it a bit, xy goes to x by 2, y by 2. This is simply scaling down whatever set I have by a factor of 2. This one again scales down by a factor of 2, but shifts by half an unit. So it makes the thing smaller and then shifts by half unit. And this one, well, it shifts by half unit along y, but also shifts by 1/4 units along x. So it moves halfway along x and up along y. So this exactly describes the copy and shift mechanism that we talked about. When we are doing this, we do this not on one point xy, but we do it to every element of S. So I get f1s, which is take every element of S, apply f1, this function, on every one of them, f2s, f3s, 3 copies which are shifted. And then you get a new S prime, which is the union of all of this. If you follow the mathematics, this is simply saying exactly what we said by pictures in the last few slides. Make 3 copies, shift them, and take them all together. That's what union really means. Now this is your new set, which I'm calling S prime, but then you just keep on repeating this by replacing S by S prime. And you keep on doing this over and over again. This is what an iterated function system is. This actually is the mathematical description of this copy-paste machine that we talked about. And technically speaking, each map contracts, it makes the thing smaller, and there's a mathematical result which says that this infinite set of iterations must converge to a final shape. And that final shape is something which will not change when you did this copy shift routine on it. And this final shape, no points for guessing in this case, happens to be the Sierpinski triangle. So for this particular iteration function system, what you get at the end in the long run is the Sierpinski triangle, no matter what S you start with. Okay. If you change the iterated function system, use different functions, maybe more than 3, and keep on playing the same game. If each of these functions happen to be a contraction, you will in the long run end up with a stable final iterate, which will give you some other picture. And if you choose your function systems properly, you can generate wonderful fractals with it. There's only one problem here. Iterating over shapes, if you wanted to do it on a computer, would be very, very computation intensive. After all, you're supposed to take every point inside the set S and apply f1, f2, f3, etc. on every one of those points. That would be impossible on a computer anyway because you have infinitely many points to deal with. But of course you don't really apply it to every point. On a computer you would apply to a large enough number of points to make this look like you're doing it to every point. But even that would be way too much work. Instead of doing that, Barnsley came up with another scheme, a randomized version of this iterated function system, which gives you the same result. This one, instead of working on a whole shape, works on individual points, so that's less work. So this is called the chaos scheme. What is this? You start with a random point inside the square and apply one of the functions of IFS. You choose it at random, but you don't choose it with arbitrary probabilities. You choose it with a set of probabilities following a very definite rule. If you know the maths, every transformation can be linearized, and the linear version has something called a determinant, which essentially is a indication of by how much this transformation magnifies your picture. Larger the final result is, the more probability you want to assign to picking that particular function. And then you keep on doing this over and over again. So for our chaos game, what we have done, the random version for the Sierpinski triangle would be like this. Imagine that we have put 3 points here, which are 3 goal posts, and we are playing a rather funny game of football. What you do is we start with a point somewhere, some random point, and then what we do is roll a dice. The dice has 6 sides. We only have 3 goals to go towards. So if the dice comes up 1 or 2, we move to the midpoint of this, of where we are. We move halfway towards the vertex A. So although I've forgotten to label them, this one is A, this one is B, and this one is C. So if you get 1 or 2, you move to the midpoint of AP. So you move halfway towards the goal A. If you get 3 or 4, you move halfway towards the goal B. If you get 5 or 6, you move halfway towards the goal C. And you just keep on repeating this over and over again. Lots and lots of times. So let's play this game. We're repeating this over and over again, lots of times. Notice that here, on 3 successive steps, we have all moved towards the goal C. Never quite reaching it because we are only moving half the distance. But that's because on 3 successive throws of the dice, we got either 5 or 6. But then I got something else. Maybe 3 or 4. So I've moved here. Next time maybe I get either 1 or 2 and I move here. And so on. And keep on doing this. The first few points will land helter-skelter. But after a while you will see that a definite shape is going to start emerging. Now, when I say while, it takes quite a long while. But before we see exactly what happens, let's get the mathematics back. The 3 maps that we saw for the iterated function system here, x by 2, xy goes to x by 2, y by 2, xy goes to this, xy goes to this. Well, each of them have exactly the same determinant, or actually same Jacobian to be more precise. And we choose each of the maps randomly with equal probability in this case. And let's see what happens if we do this. So this is what happens when you plot the first 1,000 points. You can hardly see anything right now. But after 5,000 points, this is what you get. After 10,000, 15,000, 20,000, 25,000, and you can see the Sierpinski triangle emerges slowly but surely. Now, let me give you a final example of the chaos game. I'm not going to explain to you where these functions came from. There's a typo here. It's not F1, F2, F3, F1. It should be, of course, F1, F2, F3, F4. Here are the 4 maps. How did anybody cook these maps up? The answer is trial and error. Quite a lot of trial and error, in fact. But once you know the maps, the probabilities with which you have to use them can be easily calculated using the determinant trick that we talked about. So these are the odds you're going to use: 60:1:20:19. And if you do that, let's see what you will get. The first 1,000 points, again you can hardly see anything. 5,000, a vague shape starts to emerge. 10,000, 15,000, 1,000, 25,000. You can see life emerging out of pure mathematics. It's amazing. And you can of course write a program on your own, on your computer, to draw this picture. It will be great fun to see a movie of this thing. So, in this lecture I've just touched upon the basics of what fractals are. There's a lot more to study. After all, this could be a whole semester long course. But I hope this has given you some glimpse into this wonderful world. And if you want to study more, there's always the internet. Just go on it and find out many wonderful things about this fascinating, different kind of geometry.